Wanted to start today with a poem, of all things. This was published in the New Yorker back in 1960. It's by John Updike, and it's a poem about the neutrino. And he starts by describing the neutrino. He says, "The neutrino, it is very small. They have no charge and have no mass and do not interact at all." And I like this poem because he was wrong. It's true that neutrinos are really small. In fact, they're immeasurably small at this point in physics. It's true that they have no charge, but neutrinos do have mass and they do interact, although rarely. And I like the fact that he was wrong because physicists had made the exact same mistakes at one point or another. We initially thought that neutrinos had no mass, and when they were initially proposed as a particle, Pauli lamented the fact, or is purported to have lamented the fact, that he hypothesized the existence of a particle that couldn't be detected. But 26 years after Pauli initially suggested the existence of the neutrino, it was detected for the first time. And this is the article that was published in Science at the time. I also think it's worth taking into consideration the crucial role that Michigan played, especially in the early history of neutrino physics. Crane and Halpern were the first two experimentalists to provide undeniable evidence that the neutrino had to exist in order to conserve energy. The bubble chamber, which was one of the earliest and sort of most popular neutrino experiments, was invented here at Michigan. And then the first neutrinos produced by supernovae were observed by an experiment called IMB, which was also run here at Michigan. So you're on sort of hallowed neutrino ground right now, which I think is kind of cool. So we do know some things about the neutrino. We do know it's a fundamental particle, which means it's not made up of smaller particles. We know that it has no charge, so it doesn't interact electromagnetically like the electrons say. We know it interacts incredibly rarely. So if I held up my thumbnail right now, in any given second, there are some 65 billion neutrinos, all produced by just the sun, that would pass through my thumbnail. And none of them interact with me. They just pass straight through. And so finally, we know there are three types of neutrinos. This was another unexpected feature of neutrinos. There's an electron neutrino, a muon neutrino, and a tau neutrino. And so the fact that neutrinos are sort of so hard to detect, they interact so incredibly rarely, makes us think sort of really creatively about the types of experiments we design in order to detect neutrinos. They're not only produced in the sun. In fact, they're one of the most abundant fundamental particles in our universe. They are produced by supernovae. They're produced in the interactions that occur in nuclear reactors. We actually place neutrino experiments in the vicinity of nuclear reactors in order to study those neutrinos. There's something called a cosmic neutrino background that was produced in the earliest stages of the universe. These are incredibly low energy neutrinos that at this point we can't detect, but it's very similar to the cosmic microwave background in that it would tell us a lot if we could detect it about the origins of our universe. They're also produced in our Earth's atmosphere, and finally you can make beams of neutrinos to study them, like the two that exist at Fermilab, which is where I work and do my research. And so neutrinos are part of the Standard Model. And the Standard Model we know to be incomplete because, for instance, it doesn't describe things like dark matter and dark energy. But it's sort of famously good at describing the things that it does include. And neutrinos, I think, are the one big exception. There are others, but this is the most glaring. Because, for instance, the Standard Model does not predict that neutrinos have mass, which we now know to be the case. And yet, despite the fact that we know neutrinos have mass, we still don't know what that mass is. And we don't know how to write down that mass in the Standard Model. It's essentially one big equation, and we simply don't know what the term looks like that describes neutrino mass. We have ideas, possibilities, but we're not sure which one is right now. As a direct result of the fact that neutrinos have mass, they have this cool feature in that they mix. So the neutrino is a fundamental particle, and there are three types of them. But if I produce one type of neutrino, say an electron neutrino, and send that neutrino towards a detector where it might interact, when I see that same neutrino in my detector, it may have turned into a different type of neutrino. So that neutrino that was initially an electron neutrino could have become a muon neutrino, say, or a tau neutrino. And so it's these features of the standard model that were unexpected that if we can study them and understand them better, can help us gain insight into the universe as a whole and the parts of particle physics that we have yet to describe accurately. So neutrino mixing is sort of unique, or mixing is unique to neutrinos. And so I want to spend sort of a little time trying to give you some intuition for how it works, because it's not necessarily obvious how something that is fundamental, that can't be broken up into smaller pieces, can change from one thing into another. And so I've told you that there are 3 types of neutrinos. We call these flavors of neutrinos. These are the states in which neutrinos are produced. So when a neutrino is produced, it has to have a single flavor. And when it's detected or interacts, it also has to have a single flavor. Now, I also told you that neutrinos have mass. And as you might expect, there are 3 neutrino masses. And these are sort of the stable states through which a neutrino propagates through space. So these are the states that the neutrino wants to move in. But what's so weird about neutrinos is the fact that these mass states that we call nu1, nu2, and nu3 are combinations of flavor states. So these states that have definite mass, things that you can actually measure, are not what get produced. So when you produce or detect a neutrino, that neutrino doesn't have a definite mass, which is weird, right? Mass is something tangible. Mass is something you feel like you should be able to measure. But the neutrinos that we see in our detectors don't have a definite mass. And so this is sort of a picture, a little schematic of what happens. A neutrino can be produced. At Fermilab, we produce primarily muon neutrinos because they're sort of the easiest to produce in neutrino beams. But as that neutrino, after it gets produced, moves through space toward our detectors, it picks up parts of each other flavor. So it becomes a combination of electron, muon, and tau neutrino. And the fraction of each part changes over time. At the point that we detect the neutrino, it needs to pick a flavor again. So up until the very point when it interacts in our detector, it is still some combination of flavors. But the act of detecting the neutrino itself requires it to pick a flavor. So this muon neutrino that we started out with, when it interacts again, may display as an electron neutrino. And so that's where this demo comes into play, which I have to thank the demo lab for putting together because I was really excited about it. But we can think of this mechanical system as an analogy for our quantum mechanical neutrino. So it's not a perfect analogy, but I think it does a good job illustrating how we get neutrino mixing. And so in a world where we had, say, only one neutrino, we're going to call this our electron neutrino, our muon neutrino, and our tau neutrino, these physical pendula that you can see because these are what we detect. In a world where there's only one neutrino, if I say produce an electron neutrino and let it propagate, it remains an electron neutrino. But we live in a world where there are 3 neutrinos, and they're coupled together, represented by these springs here. So in our world with 3 neutrinos, I'm trying to keep these as still as possible, if I produce an electron neutrino, represented here by putting this pendulum in motion, and we watch what happens, you'll see that very quickly the other 2 pendulums start to contribute to the motion. And in fact, the one that contributes most to the oscillations changes over time. Right now, it's mostly a tau neutrino. Now it's an electron neutrino. Now it's a muon neutrino. See? So it's changing over time. And that's because electron neutrino in this neutrino system that we have here is not a natural state of motion. This physical system has 3 normal modes of oscillation, what we can think of as the neutrino mass states. And so, for example, here's the second one because it's easiest to do here. And so you can see that this motion is extremely regular. You can predict exactly what's going to happen at any given moment in time. And there's no real beating, but it's got contributions from multiple flavors. So this neutrino mass is a combination of the flavor states that we can physically see. And so there are 2 other normal modes that are a little bit harder to demonstrate, but like with neutrinos, there are 3 in this system, as you also have 3 pendula. So the sort of first one is just this one that you might think is sort of obvious, right? And then there's a third one. This is like the heaviest neutrino mass. which is sort of like this. Again, regular motion, but it's got contributions from each flavor. So that's sort of how mixing happens. Because I need to reproduce a neutrino of a single flavor, I get these beats between types of neutrinos. And so if I detected it, say, now, I might see a tau neutrino. And so if we know neutrinos mix, the next obvious question to ask is how much do they mix? Say I produce 100 muon neutrinos, and I detect them somewhere else, how many of those will have changed into other types of neutrinos? And so we can measure neutrino mixing with sort of 3 big steps. First, you need a source of neutrinos. You either need to produce the neutrinos at beamlines, like the one at Fermilab, or you need to sit near a nuclear reactor, for instance. And then you need a detector that can detect and count your neutrinos. And so you want a detector that can distinguish between the 3 different types of neutrinos, the electron neutrino, the muon neutrino, and the tau neutrino. And then finally, once you've detected and counted all your neutrinos, you compare how many you saw of each flavor to your expectations. We have models for neutrino mixing based on what we think we understand about neutrino physics, but we're not sure if they're correct. And so if we find disagreement between our expectations and our observation, we learn something new. And right now, the sort of state-of-the-art detector for neutrino mixing experiments is something called a liquid argon time projection chamber. It's a lot of words, but it's basically a big tank filled with liquid argon that takes really, really high resolution pictures of neutrino interactions like the one I'm showing here. So for example, this is what happens when a muon neutrino interacts in one of these liquid argon detectors. The muon neutrino comes in, it's invisible to the detector because it's neutral and these detectors observe charge particles. But when the muon neutrino interacts with an argon nucleus, it produces charge particles that are products of the interaction. So you see a nice long muon track come out of the interaction. You see things like protons and other hadrons. And you get tons of detailed information about what happened. Enough information that you can reconstruct information about the initial neutrino itself, even though you couldn't see it. You can figure out its energy, its flavor, and so on. This is what an electron neutrino interaction looks like. You can see it's slightly different than a muon neutrino interaction. This is coming from a different beamline at Fermilab. That's why it's coming in from a different direction. But again, you can't see the neutrino, but you see the products of the interaction. You get an electron in this case, and then again, protons, you can get other hadrons. And the topologies can be more complicated, but my point here is you can see everything that's going on in this interaction. These are basically high-resolution cameras, which is really, really cool. So for instance, I'm going to use the laser pointer, but in this top view, these sort of 2 messy track-like things are a pair of photons that are produced by something called a pion that are pretty standard in these detectors. So in order to try and demonstrate why these detectors are the gold standard of neutrino mixing physics right now, I want to do a little case study. So we're going to look at a result from an experiment called Miniboon that was something called a Cherenkov detector. Miniboon ran for a really, really long time, and it produced a lot of results, but it also gave us one of our biggest anomalies in neutrino physics, something we really don't understand right now. This is an example on the left of an event or an interaction in Miniboon and the same interaction in a liquid argon detector. So this is that result from Miniboon. On the horizontal axis, I'm showing you electron neutrino energy, and on the vertical axis, I'm showing you the number of electron neutrinos we expected and detected at each energy. The filled-in histograms, the colored-in stuff, represents our expectations. So these are the number of electron neutrinos that we expected to see in Miniboon. And the data points, the ones with error bars, are the number of electron neutrinos that we actually saw. And so you can see that there's a disagreement between the number of electron neutrinos we observed and the number we expected. But at this point, we don't know why. We can't explain that difference. And Miniboon doesn't have enough information to explain it. And that's why one potential reason why this might be the case, people predict that there may be a 4th type of neutrino. So the question is whether the system that I showed you earlier should have a 4th pendulum. But in order to answer that question, we need more information from these interactions. And so that's where our liquid argon detectors come into play. This is the same type of interaction on the left shown for Miniboon, that older result where we don't understand the disagreement. And on the right is the same type of interaction in a liquid argon detector. And so you can see that there's just so much more information included in the LAR-TPC. Mini Boon was basically sort of a standard definition camera of these events. The LAR-TPC is a high definition camera. And so there's just a lot more that we can use to figure out what's going on and why that disagreement is happening, and hopefully decide whether there is in fact a fourth neutrino or not. So I want to return to this poem and try to take stock of where we are in neutrino physics. We know a little bit. We learned that neutrinos are detectable. That was one of the first things we figured out. We know that there's more than one type of neutrino now, but we don't necessarily know if we've observed all of them. We also know that neutrinos have mass and can mix. But that is sort of the tip of the iceberg, and there's a whole slew of open questions in neutrino physics that we're trying to answer right now. For instance, are there additional types of neutrinos? That's the result we sort of just went through. What is the mass of the neutrino? We know it has mass, but we don't know what that mass is. And we don't know how it gets its mass. There's also a question as to whether neutrinos are their own antiparticle. So whether a neutrino and an antineutrino are in fact the same exact thing. We'd also like to be able to observe those neutrinos that were produced in the earliest stages of our universe, even though they're extremely low energy. But there are really cool experiments trying to do so. And then finally, there are sources in our universe that produce ultra high energy neutrinos, and we don't exactly know what those sources are yet. And so we're also working on trying to figure out what produces neutrinos of such high energy. And then of course, there are questions that we haven't even thought to ask about neutrinos yet. I mean, we're still learning things every day. I think there's more that we don't know about neutrinos and that we know we don't know than we do know. And so with that, I will just say thank you. And if you are interested in learning more about neutrinos, this All Things Neutrino site does a really, really good job laying out sort of all the mysteries and all that we're doing to try and unravel them. So I'd point you to that if you're interested in more.
Thank you very much, Rory. Our next speaker is Noah Weaverdyck, and he will be telling us about galaxies galore, precision cosmology, and large-scale structure.
Can you hear me? How about now? Good. Okay. I'm Noah Weaverdyck. I'm a fourth-year grad student working with Dragan Huderer. And as Tim said, I work in cosmology. And we're a little less specialized than a number of the other areas of physics, a little bit younger in terms of being able to have the technology to really collect a lot of data. But today I'm going to be talking about the work that I've done with Dragan on making sure that the data that we get from galaxy surveys actually gives us the correct inferences that we want for our scientific analyses. So first off, I'll start by talking about what is cosmology. So it's the study of the scientific laws governing the dynamics and evolution of the universe at large. Okay. And so basically just the really big stuff. And stuff so big that it takes light 30 million years to go across. So much larger than the scale of any individual galaxy. And it's only been in the last 100 years that we've really been able to turn this into a science, because that was about 100 years ago when Einstein published his theory of general relativity, which allowed us to mathematically relate the shape and evolution of space itself, how it expands or contracts, to the types of energy and mass that are embedded within it. And very soon after that, we actually detected galaxies outside of our own, and so began to measure things on these scales. So I want to show you this map that's already a little bit dated. But this is a map of our neighborhood. We are right here at the very center, looking outwards. And this is from a galaxy survey, the 2DF survey. And each one of these blue points is another galaxy. Okay? So this is a pretty large-scale map, hence large-scale structure. And there's about 100,000 galaxies in here. And what we can do with this is to actually see whether this looks like the way we would expect it to look, given our understanding of the laws of physics. So one thing you might notice is that there's fewer galaxies out here on this far wedge. And that makes sense because things that are far away are fainter. It's harder to see the galaxies that are out there. But that's not all that's going on, because this is such a large scale that it actually takes 4 to 5 billion years for light from those galaxies to reach us. So we're actually looking at them as they were 4 to 5 billion years ago. And that means that they've had 4 to 5 billion years less time to aggregate mass and form galaxies. So the deeper we look, the further back in time we are actually looking. And this gives us a great data set to test our understanding, because we can look at how things, what we observe far away, and use our understanding of the laws of physics and gravity, run the clock forward, and see basically if what we observe matches what we would expect given our understanding. So to make that a little more concrete, I have here a simulation. This is actually running forward in time. Pink is high mass density, and blue is voids. And so this is running forward over billions of years, how we would expect under general relativity for mass to aggregate under the force of gravity. And you'd have many galaxies populating within these large-scale filaments. So we can take this and we can ask, does what we observe match what we expect? And if it doesn't, then there's an indication, as Rory mentioned, that there's something we're missing, that we have something to learn about gravity that we didn't know before. If it does match, then we can learn something else, because, as I mentioned earlier, the general relativity allows us to relate how the expansion of space, how that depends on time, to the types of energy and mass that are embedded within it. And so we can actually learn about what our universe is made of by seeing how this evolves over time. And what we find is that the universe is made up, seems to be made up of these 3 major wedges of the pie. So only about 5% of what we tend to think of as making up our universe is actually in that form. The rest is this other mysterious dark stuff. So the tables here in front, your neighbor sitting next to you, that's only 5% of the universe. Even the stars, the planets, everything we see. In fact, only a tiny fraction of that, actually, of that 5%, since the vast majority of that even is just distributed as interstellar hydrogen. There's about 5 times more dark matter than this regular matter. We don't know exactly what it is. It's a very active area of research. Lots of people here at Michigan are actually looking both directly and indirectly for dark matter and trying to detect what its properties might be. We know that it seems to not interact electromagnetically. That is with light. We can't see it, hence dark. But we can infer its presence through many different and fairly independent probes, and they all sort of indicate that there's about this much of it. And that's a whole talk in itself, and there's plenty of people here at Michigan who'd be happy to talk with you about that in particular. The rest is dark energy. And this is, we know even less about than dark matter. It's kind of a catch-all term for whatever it is that is driving the accelerated expansion of the universe that we see. And it seems to fill the rest of the pie here. And as far as we can tell, the data is not excellent yet, but we will be getting much better data in the next decade or 2. But so far, it just looks to be, it's consistent with, I should say, an inherent energy in the vacuum of space itself. But there's no reason that that's what it has to be, and so there's a lot of work going into trying to detect deviations from that case. But again, the data for that coming in the next few years will allow us to answer that much more precisely. So a lot of cosmology is devoted to measuring the slices of these pies, or saying if there's actually something more, if the model is not quite so simple, then how do these change, and what else can we look for to answer, to see if that's the case. One of the probes that helps us to determine this is galaxy surveys, which is what I look at. And I want to talk a little bit about the specific one that I work on, which is the Dark Energy Survey. It is probably the premier galaxy survey and will be for the next 5-10 years until a new one comes online. But it is a collaboration of 400 plus scientists from all over the world. And we collect data on this telescope, the Blanco telescope in Chile. It is beautiful down there. Here's the night sky. I'm here on the left. And just to give you a sense of scale, so this is a 4-meter telescope, 4-meter diameter. This whole building is devoted to the telescope, and the doors here come up to about our knees. We're quite a bit in front of the telescope. So it's a really big building. There's another galaxy. That's one of the Magellanic Clouds. And this telescope surveys an entire eighth of the sky, or just finished, actually, I should say. We just finished our 5.5-year run in January. And we've only just released the first year of data because there's actually quite a bit of lag between the data collection and the data release, because there's a lot of processing that goes into making sure that that data is usable. And so why is that? I'm going to talk about one piece of that pipeline, and that is all of these effects that can change, sort of contaminate the maps that we want to create that I showed you, that can contaminate our measurements of how many galaxies exist at any given point in space. So if you think about, if I look over here where there's a bunch of stars, the deeper I try to look into the Milky Way, the harder I'm going to see galaxies behind it. It's going to be harder to detect the number behind the Milky Way. So where there's more stars, you're going to undercount the true number of galaxies. So you have to account for that. There's also interstellar dust. And where there's more dust, you're going to count fewer galaxies. So you have to account for that. Here are some maps of some of these effects that actually cause us to measure a different number of galaxies than truly exist. And there's also some atmospheric effects, which I'd like to demonstrate here how that comes into play. So this is some of the most pernicious effects, actually, is that this light is coming for billions and billions of years, and then this tiny last little fraction gets completely disturbed by our own atmosphere. So the demo lab has graciously set up this telescope to peer at some artificial galaxies across the room. They've also arranged to bring in some atmosphere, and so thankfully we can all be here today. But different nights in different points of the sky, there may be cold or warm fronts that cause turbulence in the air, and not only changes the shape of the galaxies that you're measuring, but also cause them to blend together and for you to not realize that you're actually looking at more than one. So this is just one example to show you. This particular effect, there's some novel recent methods to actually correct for, called adaptive optics. And not everybody has this. The Dark Energy Survey doesn't have this, but it's a pretty cool technology where if you know the actual shape of one of the things in your field of view, then you can do some really quick mathematics to turn the blurry shape that you're really observing back into the shape, the reference shape that you know it should be. And in doing so, undo the effects of the atmosphere. So you actually end up deforming a mirror to turn that shape back into what you know it should be, and can turn those, that blurriness into a much clearer picture. So here is an example of the adaptive optics system on Keck. This is fairly new technology for astronomy. The military has been using it for a few decades, but we didn't really know about it. They've, of course, looking down, not up, and they've got a lot more money to use it than we do. So we have to do it the old-fashioned way, which is to use these maps, these measurements of effects that we think might be contaminating our data, and figure out how to use them to correct our data, okay? And so the methods to actually do that are pretty varied and have been applied and have been sufficient for the precision of data that we have thus far. But the next generation of surveys is going to be unprecedented in terms of how many galaxies they actually measure and the statistical constraints that those are going to give us, which makes tiny variations from imparted by either these contaminants or the cleaning of them much more significant. So what we're working on right now is to actually take all of these different methods that have been used and compare them on a standardized set of data where we actually know the truth. And so we run them on this simulated data and compare the different methods for how well they actually get to the true underlying cosmology that we're trying to measure. And this will be imperative for future surveys, as I said, because of the level of data that we will have. So here's an example of what that sort of looks like. Here are three things that we would be trying to measure: the expansion rate of the universe, the amount of regular matter there is, and the amount of dark matter. And to explain this a little bit, I've normalized the vertical axis to basically have this is the truth value for all three of these different cases. And this band is the confidence that we're claiming we know the answer to once we've gotten our result. And so if we tried to do this analysis without actually correcting for any of these effects, we would end up confidently claiming that the expansion rate was something that it's not. It's not so bad if you claim it's something it's not, as long as you've got very big error bars. But in this case, we are significantly biased, much greater than the confidence that we are claiming. And so that would be bad. So this is for a DES-like survey. And as I mentioned, the current methods that have been proposed are sufficient. These are two different methods that if you apply them, both of them bring your results within the band that you're claiming. And so that's good. But they have slightly different properties, and those properties we want to know for the next generation of surveys because it also allows us to potentially improve them. Furthermore, the next generation of surveys are going to dramatically shrink this band such that these will no longer be sufficient. So that's why we're doing the work that we're doing. The next generation of surveys is going to continue to make this a very exciting time for cosmology. We're going to learn a lot more in the next decade, and we need to be ready when that onslaught of data comes. With great data comes great responsibility, so that's why we're here. Thanks.
Thank you, Noah. Our third talk is by Chen, and she will be telling us about magnetic microscopy and how new techniques can measure magnetism.
Still? Oh, okay, now it's good. Yeah, wonderful. Okay, let's start. Hello, everyone. My name is Chen. I'm actually a low-energy physicist And both Rory and Noah, they are high-energy physicists. That's why I came out as the last speaker here. So I'm from University of Michigan Physics Department, and my advisor is Lu Li. So he's also sitting in the audience here today. So today I'm going to talk about how do we use a quartz tuning fork to make a torque magnetometer. So this figure shows our experimental setup. But before talk about that, first let's take a look about this picture. This actually shows a regular tuning fork. I mean, a bigger version of that. So I think some of you may have seen that before. So we use this kind of large tuning fork to help to tune our instruments. Okay. So if you hit the metal tuning fork, it will make some sound. But actually, in our experiment, we're using a much, much smaller version of that tuning fork. So they're actually made by quartz. So this picture just gives you a rough feeling like how small our setup really is. So before talking about tuning forks, first, please allow me to give some background introduction about the magnetization and also the magnetic materials. So when we are talking about magnetization, so we're usually mean something like how magnetic materials respond to an external magnetic field. So I think one most common example for the magnetization process is actually how the campus got aligned with the Earth's magnetic field. So because we have an Earth's magnetic field always in space, if you put the campus here, the needles always turn to align with the field and also point to the Earth's north pole. Okay, so that's one of the example. And the second example about the magnetization process is how those ion filings get attracted by a magnet. So this big magnet actually create a strong magnetic field here and help to magnetize those ion filings and finally attract them to the magnets. So both of these two examples, that tells us how a magnetization process works here. So now after we know something about magnetization, so the next question we're going to ask is why we care about those magnetic materials and how we can use them for. So actually there are a lot of examples. So first of all, we can always use the magnet materials, to make some permanent magnet. This is exactly the picture I took from my home. Yeah, I just collect a lot of them whenever I went to a new place. Okay, and except for that, so actually we also use the magnetic materials to make some data storage device. For example, like a floppy disk. This is super old. I think nobody of you is still using that today, right? But we are actually using the hard drives, which are actually made also by some magnetic materials. And there is another very common example is the credit cards. We made the credit cards and also magnetic stripe cards with some magnetic materials. So if you take a look at the backside of your credit card, you will find there was actually a stripe here. So this stripe is actually made by some magnetic materials and it can respond to the magnetic field. That's exactly how we use the readers to read the information from your credit card. Okay, so after know about all of these applications for magnetic materials, so the next thing I'm going to talk about is what is a magnetometer. So an easy way to understand this is if you just tear this word apart. So it's just magnet and meter, so which tells us a magnetometer is just a device used to measure the magnetic field or magnetization in the materials. So there are many examples about magnetometer, and the campus is actually the oldest example of the magnetometer. So our ancestors already used it for thousands of times to tell the direction of the magnetic field, right? And then, but in nowadays, they have many, many very fancy commercially available equipment to be a magnetometer. So this one is actually called Squid from Quant Design, and it's actually worth millions of bucks actually. But actually in our lab, we're using some other version of the magnetometer to do the measurement. So this one is actually called the torque magnetometry, so which can use to measure very small magnetization signals from the samples. So now I'm going to talk about quartz tuning forks. But before we go over about that, let's first take a look at this picture. I think many of you are very familiar with some of the branches here. So actually there are all those fancy branches for wristwatch. And I think for some of them, like Cycle and Swatch, they're still using quartz oscillators or quartz tuning fork as a time standard for many long times, right? And I think they all sell those watch for super high prices. But what's actually the secret formula inside? You can only know that after you actually open one of those wristwatch, okay? That's exactly what the scientists did. They opened the backside of a swatch here. And actually what they found inside the swatch is they found a small cylinder inside. If they further open the cylinder, they found, okay, actually inside there was a super small tuning fork there. So the tuning fork actually act as a time standard for the wristwatch. And if you take a look at the tuning fork under the microscope, So you will see that's exactly what it looks like. So people cut the quartz crystal into a tuning fork shape and also put metallic electrodes on that. So this whole thing just forms a tuning fork. So what's the secret formula for this tuning fork is actually these tuning forks, they always have a very high quality factor. So what that tells us is this figure actually shows oscillation pattern for very low quality factor oscillators. So you can see that actually this oscillator dies off in only 5 cycles. And if you further take a look at the time scale here, you can see it actually dies within 20 milliseconds, right? But if you take a look at those oscillation amplitude versus time for those tuning forks, they have very high quality effect here. You can see that they dies all the way in 31 cycles, and if you further take a look at the time scale here, you see it only dies out, within 1 second. So it's much, much longer than the low quality factor oscillators. So that's one good property for the tuning forks. So the other reason why they use the tuning fork as a time standard is the tuning fork has a very low frequency variation at room temperature, which means if you tune your watch at some time, it can last for a super long time. That's why you don't need to tune your watch every day to make it always show the correct time, okay? I think both of them are the reasons why tuning forks has been used for wristwatch for a long time. Okay, so now I'm going to answer the most important question is how do we use a quartz tuning fork to measure magnetization in the magnetic material? But before we're talking about that, the first thing I'm going to talk about is resonance. Because in our measurement, first we're going to drive our tuning fork oscillator into resonance. So I'm going to explain this phenomena by a demo, so which is actually here. So it's a 2-driven ball system. So you can see, first let me explain how the setups looks like. So we have 2 balls here. So they are connected together by a spring, right? So what I'm going to do is I'm going to use a motor to drive the upper ball, and at the same time, the lower ball will move together with the upper ball. So what I'm going to do next is I'm going to turn up the frequency of the driven force a little bit, just gradually increase it. And all of you guys have to see like what happened to this lower ball, okay? So in the middle, so the meter here shows actually how high the frequency of the upper ball is. So let's do it together. So now let me slightly tune up the frequency. Okay, so it's pretty small, frequency is small, and then you can see the upper ball actually moves with a very small amplitude, and the lower ball is also moving at the same time, right? And then now I'm going to further turning up the frequency, okay? And then you can see the lower ball moves, has a bigger and bigger amplitude, right? And I'm going all the way to here. Let's see what happened. So now at this point, I think the lower ball got the maximum amplitude, right? That's exactly what we call a resonance phenomenon. That's when the oscillation amplitude gets to maximum. So if I further turning up the frequency here, what happens next is you can see the amplitude becomes smaller and smaller. And finally, there is almost no obvious oscillation at all, right? Okay, so this demo just give you a rough feeling like how resonance looks like. So please allow me to go over the results of this demo with you again. So, okay, so that's exactly what we got in this demo. So if at the beginning, if I only drive the ball with a very low frequency, the amplitude is super small. But if I further turning up the frequency, you can see the amplitude gradually increase. And at some certain point, at some certain frequency, the amplitude gets maximum. That's exactly what we call the resonance frequency. But after that, the amplitude starts to decrease and finally goes to 0. So this is exactly how a resonance curve for a driven ball system looks like. So now let's take a look about how a resonance curve for our tuning fork looks like. So actually, it still has a similar shape. You can see when we gradually tuning up the frequency for the tuning fork, you can see the amplitude of the tuning fork was strongly enhanced at this resonance frequency. So there is a big difference between this resonance curve and the resonance curve for the driven ball system. Is actually, you can see the peak here is really, really sharp, right? So this sharp peak actually is a sign to tell us that actually this tuning fork oscillator has a super high quality factor. So that's one of the reason why we use this tuning fork in our measurement. Okay, so now please let me answer the most important question. How do we use a tuning fork to measure magnetization signal in a sample, right? So let's take a look at our setup. We have a tuning fork, and we glue a super small sample on top of one leg of the tuning fork. And then we're going to apply a magnetic field to our sample. So what happens here is we first try to drive the tuning fork into resonance. And after we apply a magnetic field, So what this magnetic field do is gonna induce a magnetization in the sample, which will actually apply a mechanical force that's pushing down the tuning fork. So when the tuning fork was actually pushing down by some mechanical force, what happens is actually the resonance frequency of the tuning fork changes at the same time. So this actually tells us if we were able to measure the resonance frequency of the tuning fork, we should be able to tell how large the magnetization signal inside the sample is. So in order to further explain this phenomena, I'm going to use a second demo. That's the tuning fork with hanging mass on that to explain how the tuning fork setup works. Okay, so let's take a look at the setup here. I have a super big version of the tuning fork. And what I'm going to do is, first, without attaching any mass, I'm going to hit the tuning fork. And I'm going to use this oscilloscope here, which actually shows the frequency in the middle screen. I'm using this one to actually measure the resonance frequency of this tuning fork. And after this step, I'm going to put some hanging mass on this tuning fork, which actually act a force on the tuning fork. And I'm going to hit it again to measure the resonance frequency again to see how the resonance frequency changes. Okay, let's do it. So I'm going to let it run. Okay, 1 second. Okay, so first. Okay, so if we take a look at what the oscilloscope gets, you can see that actually at this point, the resonance frequency is about 1080 hertz, so it's 1079 here. So the next step, what I'm going to do is I have a small piece of mud. I'm going to put it on top of the tuning fork. Okay, I'm going to firmly glue it here, and I'm going to hit it again. Okay, let's try to measure it. Okay, second time. Okay, so this is actually what we got in the second time. So you see that actually the frequency become a little bit lower than before. So this kind of small change just tell you that actually in the regular measurement for our experiments, the same thing happened is the signal change is usually pretty small. But actually this demo just helped to give you guys a feeling that actually if you put some force on the tuning fork, actually the resonance frequency changes. Okay, so now let's take a look at our real experimental setup. I think I showed this schematics at the beginning, right? So we first machine some substrate by some metal stuff, and then try to glue our tuning fork on the side of the substrate, and then put a sample on top of that. So we have a picture that's actually taken under the microscope. That's exactly how our tuning fork setup is. So you can see the scale bar tells us actually our tuning fork is only around 3 millimeters long. And to further explain at actually how small our setup is actually, you can see between these two legs of the tuning fork, there is a small gap here, right? How small is this gap? It's small enough that you can only put one piece of the hair inside. This gives you a feeling like really this one is super, super small. So there's another challenging part for our experiment is actually, in order to get this tuning fork, we have to open a lot of package for this tuning fork to get this tuning fork. But the good news is I don't need to buy many fancy swatch and to tell each of them apart to get this tuning fork. So the good news is actually a lot of companies, they just sell these bare tuning forks with a very low price. If you buy hundreds of them at the same time, each of them is less than $1. That's the good news, right? Okay. But I still need to try hundreds of times to get a good one from the vacuum cell of this guy, right? Okay. So now let me finally show you guys our experimental results. So one thing we try to use our tuning fork setup to do is we try to measure the hysteresis loop in a ferromagnetic material. So before take a look at our results, first, please allow me to explain what is a hysteresis loop. So the hysteresis loop usually means for this kind of ferromagnetic material, if you first try to increase the magnetic field and then decrease the magnetic field, the magnetization inside the sample actually, between sweep up and sweep down, they don't overlap with each other. That's how they actually form a loop here, okay? So this curve was taken by some commercial equipment in our lab. So in the next step, what we're going to do is we're going to measure the same sample, but with our tuning fork setup. And we are trying to measure the frequency shift when we try to change the magnetic field. So this figure actually shows what we got here. When we are trying to vary the magnetic field, we got this very nice bow tie feature here. And it also shows us actually the sweep up curve don't overlap with the sweep down curve. So these two pictures give you a feeling that actually we can use the tuning fork setup to measure the hysteresis loop in the ferromagnetic material. So now, please allow me to give the summary of my talk. First of all, we were able to open hundreds of packages to get this very small tuning forks. And what we're going to do is we make some tuning fork magnetometer setup with this small piece. And then we got a very high quality factor oscillator by this setup. After that, we try to measure the hysteresis loop inside the ferromagnetic material. But actually, except for that, this tuning fork is super powerful to measure some other stuff. So for example, we try to use it to measure the quantum oscillation signals in some topological quantum materials. But because I don't have enough time for that, so I'm going to maybe leave it for questions. So I think that's all I want to talk about today. So let's give the other time for all the questions. Thank you.